Imagine you're sitting in a lifeboat on the freezing night of April 15th, 1912. You're watching the Titanic's final moments. Now, you'd probably expect to hear the terrifying screech of tearing metal, right? Well, according to the survivors, that's not what happened at all. It sounded like shattering china. Welcome to This Explainer. Today, we're going to treat the most famous maritime disaster in history as a true crime forensic engineering investigation. We're stripping away all the Hollywood romance to look at the hard data, the metallurgical science, and the structural design. Because we want to understand exactly why this massive vessel failed the way it did.
So let's dive into that terrifying reality experienced by the survivors. That specific sound of breaking china is our very first and honestly our most important clue. Just think about that for a second. A 46,000-ton steel leviathan didn't sound like a modern car crash. It sounded like a fragile teacup shattering into pieces in the dark.
And that sound tells us something absolutely crucial. The Titanic didn't just quietly take on water and sink. It physically fractured. We are going to peel back the layers of physics, chemistry, and early 20th century engineering to understand exactly why a supposedly unsinkable structure literally snapped in half.
Section 1. Debunking the gash myth.
Okay, let's look at the exact moment of impact and correct a massive historical misconception. For decades, the story was that the iceberg tore a giant 300-foot continuous gash into the side of the hull. But modern forensic analysis? It tells a completely different story. The impact was actually a glancing scrape. It caused localized buckling of the hull plates and the popping of the rivets holding them together. When you add up all those separated seams and popped rivets, the actual open space letting water in was just 12 square feet. To put that into perspective, that is roughly the size of a standard front door. But here's the catch. It wasn't the size of the opening that doomed the ship, it was the location. That incredibly small amount of open space was fatally distributed across 6 separate forward watertight compartments, and the Titanic was only designed to stay afloat if 4 of those forward compartments were breached.
Section 2. The Sharpie Pendulum Test.
So, why did those specific rivets and plates fail so easily under a simple glancing blow? To figure that out, we have to head into the materials science lab. Engineers use something called the Sharpie V-notch impact test. It's pretty straightforward. You raise a heavy pendulum, let it swing down, and strike a small notched piece of metal. This measures exactly how much energy a material can absorb before it breaks under a sudden impact. And this brilliantly illustrates the huge difference between modern engineering and 1912 realities. When you run a Sharpie test on modern marine-grade steel in freezing temperatures, the metal is ductile. It absorbs the hit, it deforms, and it bends with a heavy thud. But when scientists tested steel recovered directly from the Titanic's wreck in ice water temperatures, it reacted completely differently. It didn't absorb the energy. Instead of bending, it was so incredibly brittle that it snapped cleanly in two and flew right across the room with a sharp ping.
Section 3. Molecular Flaws and Freezing Waters.
Let's zoom into the microscopic level to see what made this steel so terrifyingly brittle. It comes down to the chemical recipe. The Titanic's steel had high sulfur, high phosphorus, high oxygen, and low manganese. On top of that, in the hard-to-reach areas of the bow, the builders used these cost-saving, hand-forged wrought iron rivets, and those rivets contained massive microscopic flaws and inclusions of a byproduct called slag. Now, why does that matter to us? Well, all of those impurities effectively created a grain structure highway inside the metal. Think of it like rapid transit paths. The moment the hull experienced high stress from the iceberg, this highway made it incredibly easy for cracks to travel instantly through the metal. So here is the absolute kicker. Materials change behavior based on temperature. The Titanic steel had a ductile to brittle transition temperature of about 90 degrees Fahrenheit. Below 90 degrees, the steel lost its ability to bend and became prone to fracturing. On the night of April 14th, the North Atlantic waters were 28 degrees Fahrenheit. That is below the freezing point of pure water. In that frigid ocean, the ship's hull was effectively as fragile as that fine china the survivors heard breaking. Section 4. The watertight fallacy. While that brittle steel was the catalyst, the ultimate doom of the vessel came down to a shocking systemic design flaw. You've heard of the Titanic's famous 16 watertight compartments, right? While the term watertight was a massive fallacy. These bulkheads only went up to E-deck, which was about 10 feet above the waterline. But crucially, they were completely open at the top. This was a fatal regulatory gap of the era. basically prioritizing wide-open passenger luxury spaces over absolute safety. Because they were open at the top, a deadly sequence was locked in. First, those 6 forward compartments breach and start flooding. The massive weight of that incoming water pulls the bow of the ship downward, creating a 5 to 12 degree angle. As the bow dips, the water level inside rises until, you guessed it, it simply spills right over the open tops of the bulkheads into the next intact compartment. It functioned exactly like a tilted ice cube tray, progressive, cascading. Once the water breached the top of one wall, it was game over. Flooding just those first 6 compartments meant the ship ingested over 24,000 tons of seawater. That sheer weight completely destroyed the ship's reserve buoyancy. It made the sinking an uncontrollable mathematical certainty within mere minutes of the impact. Section 5. The final fracture. Let's follow this forensic timeline to its terrifying physics-driven conclusion. It's a slow, agonizing buildup of mechanical stress. 11:40 p.m., you get the scrape. Midnight, 5 compartments are flooding. By 12:30 a.m., the bow is really starting to tilt. And by 2:15 a.m., the progressive flooding has pushed the bow so deep that the ship reaches a 17-degree angle. That angle physically lifts the ship's massive stern completely out of the water, subjecting the brittle hull to immense longitudinal bending stresses. Engineers call this extreme stress a hogging moment. You have 46,000 tons of vessel, and a huge chunk of it is now just suspended in the air, pulling against a water-filled bow. This completely overwhelmed the freezing brittle steel. Right around the expansion joint, the metal just couldn't stretch, so it fractured. The bottom-up rupture tore through the keel, causing the catastrophic separation of the ship at 2:18 a.m. before it even slipped under the surface. Understanding this engineering truth really changes how we look at history, doesn't it? It wasn't just a giant iceberg tearing a hole in the side. It was microscopic sulfur, freezing temperatures, and open-topped walls. And it leaves us with a pretty haunting question. If those materials could have merely bent instead of shattered, if those bulkheads had just been capped at the top, how many of those 1,514 lost souls would have simply lived to tell the tale of a heavily damaged but floating ship? Thanks for joining us for this explainer and exploring the fascinating science behind the story.